Welcome to the Rich Report, a podcast with news and information on high performance computing. Today, my guest is from Kotura. We have Arlon Martin, who's the VP of Marketing at the company. So, Arlon, welcome to the show today.
Thank you. It's great to be here.
You bet. I'm glad you could join us. I saw your announcement about your demo of the 100 gigabit per second optical engine. So I've brought your slides up. Why don't we start with that, and we'll follow it with Q&A.
Great. Kotura has been in silicon photonics since 2004, since the company was formed. And we have been designing various products for the marketplace. The most exciting one, which I want to talk about later today, is for the 100 gigabit Ethernet market. But I thought I would start with just a little bit of background on Kotura, who we are and where we're located. We're located in Southern California. Monterey Park is East LA. We have around 60 or so people in the company, and many PhDs. We have many patents in the technology, probably in the order of 100 patents that have either been granted or pending. And we've been in mass production of some silicon photonics products since 2006. We sell to the top tier communication companies around the world. And we have more than a billion device hours on our product. So we're ISO certified and in mass production. And silicon photonics basically is a new technology which integrates optical functions into silicon chips, CMOS chips, built on a standard semiconductor platform, the way computer chips are built. And the goal is to provide faster data transfer in smaller packages, reducing the energy consumption, which is very important to data centers because lower energy consumption is lower heat and more density, and at the same time reduce the cost. So moving to the next slide is to really talk about the requirements of these optical interconnects for the next generation high-performance computing using WDM silicon photonics. Probably the biggest change which is happening in data centers is in the last 10 years is a transition from 10 gigabits to 100 gigabits. That started in 2008 with a standard created by the IEEE 802.3 BA, which put together the first generation standard, but it's also being driven by the new devices, switching chips and hub chips, which now have 25 gig electrical ports, and those are being channeled together into 100 gigabit lanes, both in the electrical domain and in the optical domain. And in the optical domain, these companies that are building the switching and the routing chips require lots of interconnectivity between the servers and between the switches in the data centers. And all of this connectivity is moving to 100 gigabits. The biggest request that we hear from our customers is that they want to keep the electrical and the optical in sync at 25 gig with very low power in a very small package, and to do it on a single fiber. Typically, the solution that Kotura offers is wave division multiplexing, or the shortcut for that is WDM. And that is a way of putting the 4 channels onto a single fiber. Each of the 4 channels is communicating at 25 gigahertz. Each of the 4 channels is at a different wavelength. And by using multiplexing, we combine them onto a single strand of fiber. That reduces the cost. some other architectures. In the electrical world, we have to use parallel lanes. In some optical configurations, parallel lanes must be used. But in Kotura's architecture, we use single-mode fiber, which is the smallest, lowest cost fiber available. And we use WDM to reduce the cost of the interconnectivity. And the integration is one of the big things that we do. And I think I will move to the next the next slide to show our optical engine. This was our OFC announcement. And basically, we can build 100 gigabit transceivers in 2 tiny chips. These chips are the size of a dime. They're 3 millimeters wide and 7 or 8 millimeters long, depending a little bit on the configuration for the customer. But they're on the order of 3 by 8 millimeters, so they're very small. And on these chips, we integrate the light source, which is the laser. We have the grating to set the wavelength because we use a WDM, so we use 4 wavelengths for the 4x25. And then we build a multiplexer to combine those wavelengths into a single point. This is all done on the chip. And then there is only one fiber attach to the chip to communicate to the outside world. On the receive side, there is only one fiber attach for 100 gigabits. We split the wavelengths back into their 4 channels using a demultiplexer. And then we have an on-chip germanium detector to convert the light back to electrical. All of this can be done with the electronics for distances of a few meters up to 2 kilometers, or maybe even more if requested. But at very short distances or across the entire data center for 3.5 watts. And this is a very aggressive advantage for silicon photonics, is to be able to do the integration, to build it on a semiconductor platform with CMOS wafers, the same way we build microprocessor chips and other chips, and to package them in a very similar way than we package the electronics. So this enables low cost, it enables low power, and it improves the density of the switches and the routers in data centers. I have one chip. I'm moving on to the next slide. I wanted to show an example of how these chips can scale. I've mentioned before that using wave division multiplexing, we get 4 channels onto a single fiber. But that's not at all the limit. In the telecommunication world, it is possible to put 100 or more channels onto a single fiber. It's kind of like listening to radio stations or TV stations in the air, is that you can change the frequency and pick up a different station. In the optical world, we do the same thing with colors of light. We use a slightly different color, we change the wavelength, and we send a totally independent channel over the same fiber. We can't do that in the electrical world. And in the optical world, though, we do, and this is an example of a chip that is very tiny, a half inch on a side, roughly, and it is 40 channels, and we can demultiplex. There's only one fiber attach, one fiber transmission, demultiplex those into 40 independent channels connected to detectors, which are capable of running at 40 gigabits per second. And so this is an example of a single chip that would support a terabit of transmission. So I want to move to the summary, and then we can take a few questions. So silicon photonics can scale at 100 gigabits, which is where we're starting. And some of the early designs were very not built on silicon photonics. Some of the early 100 gigabit designs were very power hungry because they were not using silicon photonics. And it caused them to be in a large form factor, the size of an iPhone, to be honest. That CFP form factor is almost the size of an iPhone. When in reality, we could put all these things into the size of a flash drive memory stick. And Kotura's chips do that. And in the future, the big advantage of silicon photonics is our capability to migrate from 100 gigabits to 400 gigabits to even a terabit on a single chip, and to enable compact terabit packaging options for communications between CPUs and memory for chassis-to-chassis communications, backplane, as well as data center distances of up to 2 to 10 kilometers. So that is a summary for Kotura, and I appreciate any questions that you might have.
Well, thank you for that, Arlen. I was curious as you were going through this. This is something you've demoed, right? This is not a generally available technology, correct?
Yeah, so today we are selling chips into the first generation 100 gigabit CFP packages that are so we are selling products into this space today, but this market is small because the millions of transceivers today are at either 1 gigabit or 10 gigabits. Right now, the 10 gigabit transceivers are on the order of 5 million units per year worldwide in the 10 gigabit market. But the volume of the 100 gigabit transceivers is still a few thousand per year. And so some of the early designs were the size of an iPhone. And yes, we are sold into those. But the product that we showed and the chips that we showed at OFC are for mass production in the 2013 timeframe, when the volumes will go from a few thousand and to reach 1 million or more, and they will be in the size of packages that are roughly the size of a memory stick. And so we are early. We are showing the technology, but we're early in this transition from 10 gigabits to 100 gigabits, which will be happening over the next, in a major way, over the next 3 to 5 years.
Sure. Like, so when 100 gig Ethernet switches become commonplace and economies of scale kick in, you guys will be ready with this technology, sounds like.
Exactly. Yeah. And not just the Ethernet space, but also proprietary interconnections that are from board to board and rack to rack inside a supercomputer or even inside the rack itself.
I'm glad you brought that up because I was reading your release and it talked about how multi-core, right? We can get incredible compute density in a rack now. Is that kind of driving how optical engines, the requirements that your customers are? Because you're quoting some numbers here that you might need as much as 600 gigabits out of a single rack.
Yes. So what's the big thing that's going on in the data center marketplace is the transition from 1 gig ports to 10 gigabit ports on the front of each blade. So in a data center, and we have a very stylistic picture there. I think it's on view graph number 3 of a data center. But a data center would have racks of servers. And each rack would have 40 blades. In some cases, companies are talking about expanding that to 80 blades. But today, most of them have 40 blades. And on the front of each one of those blades are two 10 gigabit ports that run to a switch, and that switch might be in the middle, it might be at the top of each rack. And those switches with 80 10 gigabit ports will have 100 gigabit ports that are part of the data center fabric, a part of that interconnect that goes across the data center. So the switches that we were talking about, the cluster switches, the rack switches, are beginning to, and the routers, of course, are all beginning to use 100 gigabits as the common currency of traffic running across the data center. So those are the spots that we're really looking at is how dense can those hubs and router chips be, and how dense can these switches be in terms of sending 100 gigabits across the data center. Did I capture the answer to that? Hello?
Oh, I'm sorry. I was on mute.
Oh, okay. I thought maybe I had lost it.
I was blabbing away on my question there.
Okay.
We'll cut this together. I was going to ask you about the importance of power efficiency in your market, because someone was describing to me some of the future exascale requirements, and they put envelopes on how much could be spent on storage as far as a percentage of power. Um, and they actually said that powering all these lasers for the interconnect actually adds up to a sizable amount. Are you running into that, or are they saying that, you've got to bring down the power envelope?
Well, that's an excellent question. The power in the transceiver is comprised of several parts. So the quick answer to that is yes. The reason today's 100 gigabit architectures are the size of an iPhone is because they use on the order of 20 watts. And 20 watts is a pretty big number for the power of a transceiver. Where we want to get that to is 3.5 watts, which is a spec, and there will be applications where we can do much less than that. But fit it into, we call it a QSFP package, and that package was designed for 3.5 watts. The power enables the density, because if the package has 20 watts, it needs to be large enough to get rid of the heat so that its own components do not overheat and cause problems in the data center. So the power consumption is related to the heat that the data center generates. So of course, on one level, it is the cost of how much electricity do I need, because I may want to build my data center next to a power supply or a river or something to cool it. But on the other hand, so if you can design devices that don't generate the power in the first place, then you can put them closer together. You can put more of them into a single rack, and you are not generating that amount of heat. The reason ours only consumes 3.5 watts is that we're able to use, there are a lot of electronics chips inside that QSFP package in addition to the optics. And the electronics chips are used to drive the modulator, to do error correction, to clock and data recovery, to communicate, lots of things to the outside world. Those chips with our technology are able to be designed in pure CMOS. And pure CMOS chips are consume less electricity, less power than silicon germanium or gallium arsenide. Many of the first generation designs are using individual components that are designed in technologies because they need to be very fast and they need to have very strict performance requirements. And the optics portion is not very good. So they're requiring components that are built in either silicon germanium or gallium arsenide, which consume a lot of power. So they're big.
Yeah. So I guess kind of a wrap-up question here, Martin. You noted that there's going to be there is headroom in what you guys are doing. Do you foresee in the near future, are you coming up against any laws of physics or walls that you won't be able to scale with where the industry is going, or what do you foresee there?
Basically, we see one of the advantages of the WDM architecture, of the wave division multiplexing architecture, is the ability to put more and more channels onto the same fiber. And so we're starting with 4. This is many channels have been used in the long haul networks, but not in data center applications. So this will be probably the first, one of the first times in which WDM wave division multiplexing is being used in data centers. And one of the abilities of our technology is to move from 4 channels to 8 channels. So instead of 2 ports, if they have a 200 gig link, instead of using 2 ports on the board space, they can just use 1 port. And then there are customers that want 400 gig. So the ability to scale from 100 to 200 to 400 is important. And one of the beauties of the silicon photonics technology is to enable that migration path in a very graceful way. Still a single fiber, still a single product, but enable a migration path to 200 and 400 gigabits per second.
Well, sounds terrific. Well, Arlon Martin, I want to thank you once again for coming on the show today.
Well, thank you so much.
Hey, it's been my pleasure. Okay, folks, that's it for the Rich Report. Stay tuned for more news and information on high-performance computing.